Welcome to the second introductory video for Module 4B. In this video, we will introduce the von Mises stress theorem. You may have already seen references to this stress theorem in some of our FEA work. In the next module, we'll take a deeper dive into the various failure theorems, of which the von Mises stress is the typical one used for ductile materials. The von Mises failure theorem is also called the distortion energy theory. The ingenuity of the von Mises theorem is that it combines all the stresses on a specific stress element into a single normal stress that can be compared to the material's yield strength. The von Mises stress can be calculated either from the principal stresses or directly from the applied stresses. In most of our applications for this course, we will use the 2D von Mises stress formula, but be aware that there is one for 3D applied stresses. As noted in the earlier slides, as engineers, we need to determine the worst case stresses applied to a component. At a minimum, we need to identify the location of the maximum normal stress and the maximum shear stresses. For each location, we should develop a stress element. Then, we'll use the stress element to find the von Mises stress for each location. The location with the highest von Mises stress is where the worst case stress occurs. Use this stress for your factor of safety calculations. Often, we will verify our hand calculations with FEA. But note that both are needed for a thorough stress analysis of a component. We have already covered the shear and moment diagrams to be created when we encounter bending stress with transverse shear stress. In most applications that we encounter for this course, these will be sufficient. When you encounter applications with multiple torsional loads, you may need to create a torsional diagram to define the maximum torsional shear stress. This is common for a shaft application where there may be multiple gears or pulleys on the same shaft. We have looked at this previously, but we want to remember that changes in geometry on a component generally result in locations of stress concentration. That is, your highest stresses will usually occur in these locations. These include locations where the geometry includes grooves, holes, and at the radius at a change diameter in a step shaft. In this example, we have only one normal stress and one shear stress. Thus, we know that sigma 2 is equal to 0. Note the stress element and the moored circle. By the way, these were created with an online calculator for drawing moored circle. Note the link here. You can use this tool for your homework where you are required to create moored circle. Here is another special case of moored circle. In this application, there is only a single normal stress in the x-axis. Note that sigma y and tau xy are both 0. In this case, sigma 2 and sigma 3 both equal 0. You can try out the calculator tool linked on the previous slide for different stress setups and see what effect they have on the output of moored circle. That's it for this video. In class, we will practice creating moored circle for a biaxial stress element with shear stress. Thanks for watching.